So we're now going to look at what happens when you integrate a function around a simple closed curve, gamma, when inside that curve there's just one singularity. And it turns out that the answer is always 2 pi I times b1, where b1 is that term in the Laurent series for that function and that singular point. So we're going to use Cauchy's theorem to help us do that. So what we're going to do is, rather than consider this integral here, which we don't know what the answer is to, we're going to consider this contour here. Now we know by Cauchy's theorem that since this contour here we're neatly avoiding the singularity, it's still a simple closed curve. This contour here, so I write it as a, b, c, d, e, f of the function, must equal 0 by Cauchy's theorem. So we then can analyze this line integral. You can sort of divide it up into sections. So we've got the bit from E round to A. So I'll then write this thing here. It's the integral from E to A of, then it's from A to B, then it's around, B to D, just around the little circle. And then D to E. So now we consider the limit as A gets closer and closer to E. So as A gets closer and closer to E, D and B also get closer and closer. So what we can say is that this integral here, which is in this direction, cancels out this integral here. Okay. So we can cancel out this integral is equal and opposite to this integral, which means that we're left with the result that this integral, really, as A gets closer and closer to E, is really the integral we're after. We're after this integral around here without a gap. Okay, so the integral we actually want is going to be equal to the integral around here. So it's a clockwise, sorry, I said that wrong. It's this integral here plus the clockwise integral around here is equal to 0. So that means that the integral that we actually want, let's just call the integral we want I, is going to be the integral from B to D around this circle. F of Z. Now, this is a clockwise integral. Normally we do things anti-clockwise. Sorry, I was going to write this plus, sorry. This is equal to minus the clockwise integral, which means it's equal to plus the anti-clockwise integral, which is the normal direction. So, okay. So basically what we're saying is that the integral around this singularity is the same as if I just take a circular integral around the singularity. Effectively, I can shrink the contour so that I just get a circle surrounding the singularity. The integral will be the same. So next I want to evaluate this integral. So this integral is going to be the integral of f of z dz around the little circle which I called C before. Now what I can do is write, I'm going to call this z0 now, and I can write z equals z0 plus r e to the I theta, which means that dz is equal to, well, r is not going to change, I'll just have a circle, so r times I times e to the I theta d theta. Okay, so I'm going to integrate around a little circle centered on z0. Okay, so I change variable and just say, right, so that means that my theta is going to vary as I'm going around the circle. The theta is going to vary from 0 to 2 pi. And now what about my f of z? Well, f of z we can write as a Laurent series. Now, as we've got a closed curve, remember the Laurent series looks like a0 plus a1 z minus z0 squared plus so on, plus b1 over z minus z0 plus b2 over z minus z0 squared and so on. Okay. Now all of these terms are analytic, so when I integrate around a closed loop, there's no problem with those, they're just 0. So the only ones I have to be careful about are these ones, the b1 over z over z minus z0, so the b2 over z minus z0 squared and so on. Okay. So I can integrate term by term. So let's just do the general term. Let's integrate bn over z minus z0 to the n. And I'm integrating dz, I'm writing dz as ir e to the I theta. And this z minus z0 is just r times e to the I n theta. So I can rewrite that as r to the n times e to the I n theta. Okay, so this is an easy integral to do. If n is not 1, then I get bn times I times r to the 1 minus n, and I need to integrate. The only thing left in the integral is e to the I theta 1 minus n d theta. Okay, so this is the n not equal to 1 case. If n is not equal to 1, I can bring this down, and hopefully it's easy to show this is equal to 0. Okay, so just quickly, I get e to the I theta 1 minus n divided by I 1 minus n, evaluated between 2 pi and 0. Obviously, this is an integer. When I put 2 pi here and I put 0, I get the same thing. So this is 0. If n is not 1, this is 0. But if n is 1, what happens? Well, if n is 1, this cancels with this. Okay, n is 1, the r's cancel, you've got e to the I n theta, that cancels, e to the I theta cancels e to the I theta. So the only thing you have left is b1 times I. So the integral of b1 times I between 0 and 2 pi is simply 2 pi I b1, which is the result we want to prove. So the B1 is given a special name. It's called the residue. The residue, it's called that because the residue is what you have left when you evaporate something. So for example, if you have a beaker of salty water and you boil away the water, the residue is what you have left, the salt.